All right, philosophy class, this is 1.3, classical logic, semantic validity. Remember, with semantic validity, what we're talking about is if you make all the premises true, can the conclusion be false? Not is the conclusion false, but can the conclusion be false? And if that's true, then you have an invalid argument. So semantic validity. First, let's talk about an interpretation. An interpretation, we're talking about assigning true and false values. That's what the interpretation means. So V here is going to be a function that assigns every propositional parameter and formula either 1 or 0. 1 being true and 0 being false. And in classical logic, you cannot assign them both. So it's either true or false. It can't be both true and false. So 1 or 0. And here's the way that we assign them. Going from 1 through 5, these are our connectives. The V, the truth value of not A is 1. In other words, not A is true if A equals 0 or A is false. Otherwise, 0 is false. Otherwise, not A is false, right? So not A equals 1 if VA equals 0, and it's 0 otherwise. Not A is true if A is false, otherwise not A is false, right? That's how to read that. And I'll show you a little bit more what that means later. A and B, remember A and B is this guy right here. A and B equals 1, it's true, if A equals B equals 1. In other words, A is true and B is true. If both of them equal 1, if they're both true, then A and B is true. Otherwise, A and B is false. A and B is 0, right? So if A equals 0 or B equals 0, or both equal 0, A and B is false. It equals 0. A or B, the V of A or B equals 1. If either V of A equals 1 or VB equals 1. So if A is true or B is true, either one of those can be true, and A or B is true. Otherwise, A or B is false. So in other words, if one of these guys, at least one of them is not true, then this is not true. If A then B equals 1. If A equals 0, in other words, A is false, or if B is true. Otherwise, if A then B is false. This one seems, I know, a lot less intuitive. This one is a lot harder to see, and for good reasons. I think in one of the bonus materials, I'm going to explain a little bit more why that's so counterintuitive. But if it seems super confusing, go back and watch the one before this, 1.2, and when you get to that, the circles, the little Venn diagrams will help you to see it a little bit better. A, if and only if B is true, if A equals B. Otherwise, it's false, right? So if A equals 1, then B better equal 1. So in other words, if A is true, then B better be true. If A is 0, then B better be 0. In other words, if A is false, then B is false. And that would make this true. So remember, 1 is true. If I assign it a 1 value, then it's true. If I assign it a 0 value, then it's false. So what does all that mean? That sounds probably a little confusing. Here, let's break it down. All right. So the first one, not A equals 1 if A equals 0, and 0 otherwise. What does that mean? Well, if all you have is A, then you have two options. A can either be true or false, right? So we're starting off with A, true or false. And then looking at this not, I then apply it to the A, and I see what happens based on this rule. This rule says if A equals 0, then not A equals 1. Here A equals 0, so not A right here equals 1, right? Otherwise, not A equals 0. Here is otherwise, right? A equals 1 here, so not A is 0. So if A is true, then not A is false. This is called a truth table. And the truth table, you assign all your variables here, all the either a 1 or a 0, in all the different ways that you can assign them, and then see how that shakes out with the connectives. Here, It'll make more sense when you're looking at this one. All right. So this one is a and b equals 1 if a equals b equals 1 and 0 otherwise. So what are your options here? Well, a could equal 1 and a could equal 0, right? If a equals 1, then b can either equal 1 or b could equal 0. And if a equals 0, again, b could either equal 1 or b could equal 0. So those are all the options. Those are all the different combinations that you can make. And based on this rule, if a equals b equals 1, then a and b equal 1. So here is a and b equal 1, so a and b equals 1, right? 0 otherwise. For the rest of these, there are zeros. So the rest of these are the otherwises. So these are 0, 0, 0. Right, and if you want to, you can check down here and see that it makes sense. A and B, remember we said you're in here. You're in this land right here. If A equals 1 and B equals 1, if A and B are both there, right, then A and B is true. If you just have A, if you're just over here, then you don't have B, then you're not in this area. If you just have B, this line, if you're just over here but you're not in A, then you're not in this guy, right? So this is false again. And if you're in neither of these, if you're outside of them, then of course you're not in here. So of course this is false. A or B. So same thing though, you're worried about what are all the different combinations I can make and what's going to happen based on this rule right here. So those are your different combinations. When A equals 1, B can either equal 1 or 0, and when A equals 0, B can either equal 1 or 0. And there's no other combinations that you can make. So this says A or B equals 1 if either A equals 1 or B equals 1. So in other words, A or B is true if at least one of these two things are true. Here they're both true, sweet, 1. Here one of them is true, 1. Here the other one is true, 1. Here neither are true, so 0, right, false. And what this, remember what A or B is, says you can be in here, you can be in here, or you can be in here. The only place you can't be is out here. So A and B, I'm in here, good. I am in both A and, I'm sorry, this is both A and B, good. If you're just in A, good. If you're just in B, good. But if you're outside of both of them, bad. If A then B equals 1. If A equals 0 or B equals 1. So let's assign these all again. 1, 1, 0, 0, 1, 0, 1, 0. Alright, so remember what we mean when we say if A then B means if you are in the A, then you have to be in the B. So you can't have A without B. If you're in the A, you must be in the B. Everything else is fine. Right? Everything else has nothing to do with it. So if A equals 0, right? So if you're not in this circle at all, you don't have to worry about it. You know that this is true. If B equals 1, you know that this is true. That's why this is this. That's why this is this rule. That's why the rule is this way. So the first one, you're in B. B equals 1. Perfect. Second one, you're in A equals 1. So you're in A, but you're not in B. Oh, you're in the bad man zone, right? So no, that's a 0. That's false. Here, these last two, you're outside of this circle, so you know you're good. So both of these are 1. That's kind of why if A then B is the way that it is. And then the last one, A if and only if B, 1, 1, 0, 0, 1, 0, 1, 0. Remember, A if and only if B equals 1. What that means is, if you have A, then you have B, and if you have B, then you have A. So you have to if you have one, you have to have the other. If you're missing one, you can't have the other. So either one of these is fine, but you can't have one without the other. So here you have one with the other, perfect. Down here you have neither one of them, perfect. Right, you're in this area over here. But in here, you have one without the other, that is false. So those are the truth tables. That's how you can tell what is valid in these arguments. And by the way, you can make these a lot longer if you want to. You could do A if and only if B, or C or something like that, and see how they all hash out. It'd just be a lot longer truth table. All right, so this guy right here means entails, but for semantics. So remember we talked about semantic validity and proof theoretic validity. Right now we're talking just about semantic validity. If you assign true to all the premises, can the conclusion have false? Can the conclusion be false? Now, if you have all the conclusions true, remember this sigma, this Greek capital letter, stands for a set of formulas. All right. So a set of formulas and the premises, the things that you're going to use to get to the conclusion. If this set is all true, and A cannot be false, then sigma semantically entails A, right? It entails A. So in other words, you can conclude A from sigma. Sigma entails semantically A if and only if there is no interpretation, there's no way of assigning true or false, right, to the variables. There's no interpretation that makes all the members of sigma true and A false. We've already talked about sigma being a set of formulas. This entails the same thing as semantic consequence. That's what that means. And if you want to say that's not true, that it does not entail A, in other words, that you assign all the formulas in here true, and then this can come out false, then you just throw a slash through it. Sigma. So that means it is not the case that sigma entails A. This is less important, but if sigma is empty, in other words, if there are no premises and A is still true, in other words, there's no way to assign A a false, then we call that a tautology. You may wonder, how is that possible, right? How could you have nothing and still prove something, right? Well, that would be something like, if I want to say either P or not P, right? And if I assign P a 1, then this not P becomes 0, right? So at least one of these two are true, so this is true. And if I assign P as 0, then the not makes this a 1, right? So at least one of these two things are true, so this is true. There's no other way to assign P a value, so this whole thing, A here, let's say that equals A. This is a tautology. There's no way to assign these true or false zeros or ones and have A equal 0, have A be false. And that's it for semantic validity.